Okay, so welcome everyone to today's IAMP One World Mathematical Physics Seminar. It's a great pleasure to introduce today's speaker, Paweł Duch from Adam Mickiewicz University in Poznań. And the title of today's presentation is Flow Equation Approach to Singular Stochastic PDEs. So Paweł, we're looking forward to your presentation.
Thank you for the introduction, and I would like to thank all the organizers for the invitation to speak at this seminar series. So my talk will be about a new framework for singular SPDEs, that is singular stochastic partial differential equations. Stochastic PDEs are used to model many systems with some random or chaotic forcing. Most important stochastic PDEs arising in physics are ill-posed in classical sense. One calls such equations singular. Giving mathematical meaning to such equations is a non-trivial problem, and usually it involves some regularization and renormalization of the equation. In the talk, I would like to present a new approach to singular SPDEs. The approach uses ideas from renormalization group theory and is inspired by the approach to SPDEs developed earlier by Kupiainen. The novel aspect of my approach, which greatly simplifies the analysis and allows a systematic treatment of a large class of equations, is the application of a certain renormalization group flow equation. The flow equation plays an analogous role to the Polchinski equation in quantum field theory. In particular, I solved the renormalization problem using ideas from the simple proof of perturbative renormalizability of QFT models given by Polchinski. My technique is applicable to a large class of singular SPDEs with fractional Laplacian, additive noise, and polynomial non-linearity. The technique covers equations in full subcritical, that is, super-renormalizable regime. The method does not use any diagrammatical representation, and in particular, it avoids all the algebraic and combinatorial problems. Here is the plan of my talk. So I would start with an introduction to singular stochastic partial differential equations. And I will summarize some important results in this area. Then I will discuss the class of singular SPDEs to which my approach is applicable, and I will state the main result of the talk. In the last part, I will discuss the idea behind the flow equation approach, and I will give you the key elements of the proof of the main result of the talk. In general, a singular SPDE is any PDE with some random terms or coefficients which cannot be solved using classical tools from PDE theory. The problem is the singular nature of sample paths of random fields and lack of regularity of the solution. The solution is expected to live in a function space which does not allow to define the products that appear in non-linear terms of the equation. Because of this, it is not even clear what it means to be a solution of a singular SPDE. Some singular SPDEs can be made sense of using certain non-linear properties of the random fields. As we will see, often renormalization of nonlinear terms is required. Before I will discuss examples of singular SPDEs, let me talk briefly about the stochastic heat equation, which is a linear and regular equation. Stochastic heat equation is a parabolic PDE. T plays the role of time. For simplicity, I assume that the spatial variable lives on a d-dimensional torus. The fourth term that appears on the right-hand side of the equation is the so-called white noise. It is a random and irregular object. By definition, the white noise is the unique Gaussian random variable valued in the space of Schwartz distributions, such that its mean vanishes and its covariance coincides with the Dirac delta. So you can think of the white noise as a randomness that is completely uncorrelated in both space and time. Because of the singular nature of the white noise, it cannot be evaluated at a point. So the formulas I gave you are a bit formal. However, one can easily make sense of them. In particular, the weak formulation of the stochastic heat equation poses no problems because this equation is linear. Regular SPDEs that I will present on the next slide can be viewed as perturbations of the stochastic heat equation. And to understand the singular nature of these equations, it's instructive to first know what is the regularity of the solution of the stochastic heat equation. And to this end, we shall use the so-called Besov spaces. So without going into the definition of the Besov space, one can view the Besov spaces as a generalization of the classical Hilbert spaces. In particular, for positive alpha, the Besov space C alpha coincides with the classical Hilbert space. For negative alphas, the Besov space C alpha consists of distributions. In particular, for example, the Besov space with regularity -3/2 consists of distributions which can be represented as second derivatives of 1/2 Hilbert continuous functions. In this talk, I will use the so-called parabolic Besov spaces. In parabolic Besov spaces, one treats the time variable differently. In particular, the derivative in the time direction decreases the regularity not by 1 but by 2. Because of these special properties, the parabolic Besov spaces play nicely with the parabolic differential operator that appears in the stochastic heat equation. In particular, the inverse of this operator improves the regularity by 2. It turns out that the regularity of sample paths of the white noise measured in the parabolic Besov scale are negative and slightly worse than 1/2 of 2 plus d, where d is the spatial dimension. Combining this fact with the smoothing effect of the heat kernel, we determine the regularity of the solution of the stochastic heat equation. It turns out that in dimension 1, the solution is a Hilbert continuous function with exponent almost 1/2. If the spatial dimension is greater or equal to 2, then the solution is not a function, but only a distribution. Okay, so now I would like to give you two examples of singular SPDEs. So the first example is the so-called dynamical phi-4 model, which is obtained by perturbing the stochastic heat equation by the cubic nonlinearity. Okay, you may wonder why an equation with a cubic nonlinearity is called phi-4 model. It turns out that this SPDE is closely related to Euclidean quantum field theory model with a quartic interaction vertex. More precisely, the dynamics generated by this SPDE preserves the measure of the Euclidean phi-4 model. Because of this fact, this equation is sometimes called the stochastic quantization equation of the phi-4 model. Let me analyze this equation in different numbers of spatial dimensions. In the noise column, I listed the regularities of sample paths of the white noise. The numbers in the next column are the regularities of the solution of the stochastic heat equation. That is the equation without the nonlinear term. Assuming that the white noise is the most irregular term on the right-hand side of the equation with the nonlinear term, it's reasonable to expect that the solution of the nonlinear equation will have the same regularity as the solution of the linear equation. Okay, so suppose that this is the case, and now consider different numbers of spatial dimensions. So let me start with dimension 1. We expect that the solution is almost 1/2 Hilbert continuous. The cube of a Hilbert continuous function is Hilbert continuous with the same exponent. So our guess about the regularity of the nonlinearity is 1/2 minus epsilon. This is consistent with our assumption that the noise is the most irregular term on the right-hand side of the equation. And in fact, the dynamical phi-4 model in one dimension can be quite easily solved in the Hilbert space with regularity almost 1/2 using the Banach fixed point theorem. The situation is a bit different in dimensions greater or equal to 2. We expect that the solution is not a function, but only a distribution. Because multiplication of distributions is not a well-defined operation, the equation is singular. Using a certain renormalization procedure, in certain situations, it may be possible to define the cube of a distribution. If this is the case, then the regularity of the renormalized cube of a distribution is equal to 3 times the regularity of the distribution. So we expect that the nonlinearity in dimension 2 has the regularity minus 3 epsilon. In dimension 3 has regularity minus 3/2 minus 3 epsilon. And in dimension 4 has regularity minus 3 minus 3 epsilon. We see that in dimensions 2 or 3, the expected regularity of the non-linearity is better than the regularity of the noise. We say that equation is subcritical or super-renormalizable. The situation is drastically different in dimension 4. The same reasoning in dimension 4 suggests that the non-linearity has a slightly worse regularity than the noise. So the noise is not the most singular term on the right-hand side of the equation. And in particular, there is no reason to expect, or at least we do not know it, whether the solution of the nonlinear problem has the same regularity as the solution of the linear equation. So the phi-4 model in 4 dimensions is not subcritical. In fact, it's critical. It's exactly on the borderline. At the moment, there is no general framework that can be used to give meaning to equations which are not subcritical. And because of that, in this talk, I will only consider the dynamical phi-4 model in dimensions 2 or 3. The second example of a singular SPDE that I would like to present is the KPZ equation. This equation describes fluctuations of the height function of a growing interface. The KPZ equation is subcritical, and it's subcritical only in dimension 1. And in this talk, I will consider only this case. So, are there any questions at this stage?
I don't see any question. I think.
Okay, let me continue. So now I would like to present some important results obtained in the area of singular SPDEs. So I will not give you a comprehensive overview. Instead, I will just list a few selected results. And I will start with the dynamical phi-4 model in 2 dimensions, which is perhaps the simplest example of a singular SPDE. So as I said before, the solution of this equation is not expected to be a function, but only a distribution. Because of that, it is not clear how to make sense of the cubic nonlinearity. To address this problem, we will first study this equation with the noise replaced by some regular noise, say some smooth noise zeta. Later, we will consider a sequence of smooth noises approximating the white noise xi, and a certain divergent sequence of counter terms C. And the goal will be to prove the convergence of the corresponding sequence of solutions. So I will present certain argument that allows to solve this equation that was originally proposed in 2003 by Da Prato and de Bush. And this argument is based on the following ansatz for the solution phi. The first term on the right-hand side of this ansatz is the solution of the linear equation with only the noise term on the right-hand side. The second term, denoted by psi, is called the remainder. We expect that as the noise zeta approaches the white noise psi, the process z is the most irregular part of the solution phi, and the remainder psi has much better regularity than phi. We also introduce the so-called renormalized square and cube of the process z. Note that these objects involve the counter term c, which will be fixed later. The remainder psi satisfies the following equation. It turns out that psi, the solution of the equation for the remainder, is a continuous function of the so-called enhancement of the noise. The enhancement of the noise consists of the noise, the square of the process z, and its cube. The solution of the original equation phi is also a continuous function of the enhancement. Note that the process z is not a part of the enhancement, because z is a simple linear and continuous function of the noise zeta that is included in the enhancement. The renormalized square and renormalized cube are also functions of the noise zeta. However, these functions are not continuous as functions between the spaces in which these objects without cutoffs are supposed to live. Now let us consider a sequence of noises approximating the white noise psi, and assume that the counter term is equal to 1/3 of the expected value of the square of the process z. This counter term diverges logarithmically as kappa goes to 0. Recall that the process z is Gaussian. Then with this choice of the counter term, the renormalized square and cube coincide with the so-called weak powers of z and converge as kappa goes to 0 in these Besov spaces. This implies that the enhancement of the noise converges because the solution of the original equation is a continuous function of the enhancement. The solution also converges. We call the limit phi 0, and we interpret phi 0 as the solution of the singular SPDE. Note that the solution is defined indirectly. You first solved the regularized and renormalized equation, and then we took a limit. The Prato and the Bush trick does not work in the case of equations which are more singular. For example, it doesn't work in the case of phi-4 model in 3 dimensions or the KTZ equation. Solving these equations was a long-standing open problem that was solved for the first time by Martin Heirel in his work about regularity structures. Another approach was proposed by Gubinelli, Inkeller, and Perkowski, who used paracontrolled calculus. Yet another approach was developed later by Kupiainen, who used ideas from a renormalization group. I will discuss the approach by Kupiainen later in this talk because it's related to my approach. let me mention that in all of these approaches, one expresses the solution. There are many possible choices for the enhancement, and different choices are made in all of these approaches. But in all of these approaches, including my approach, the convergence of the solution of the regularized equation follows from the convergence of the enhancement. The construction of the enhancement may be very complicated in the case of models which are close to critical. A systematic theory that allows to treat equations close to critical was developed only recently in a series of papers by Brunet, Chandra, Chevriev, Kairen, and Zambotti. Actually, these authors developed a very general framework that allows to treat virtually all subcritical singular SPDEs with local differential operators. Their approach applies, for example, to the dynamical 5-4 model with colored noise. The assumption is that the sample paths of the colored noise are slightly more regular than the sample paths of the white noise. Because of this fact, this equation is subcritical, but potentially very close to the standard 5-4 model in 4 dimensions, which is critical. The main result of this talk is in a similar spirit. However, I am considering a different class of models, which I would like to introduce now. So I am considering a general class of models, and I developed a systematic theory that allows to treat all of equations from this class. The class includes equations with additive white noise term and polynomial non-linearity. In order to emulate non-integer dimensions and consider equations close to critical, I study equations with fractional Laplacian. In this talk, for concreteness, I will restrict attention to a particular family of equations, which are called the dynamical 5-4D sigma model. The equations in this family have cubic nonlinearity and are driven by the space-time white noise. The dots stand for counter terms that are needed to renormalize the nonlinearity. Different types of counter terms are needed in different numbers of spatial dimensions. In this talk, for concreteness, I will assume that the spatial dimension equals 4. So this equation is posed on the 4-dimensional torus. I impose 2 conditions on the parameter sigma, the order of the fractional Laplacian. Sigma has to be less or equal to d, the spatial dimension, as otherwise this equation is not singular and can be solved using classical tools from PDE theory. Moreover, I require that sigma is greater than d over 2, as otherwise the cubic nonlinearity is potentially more irregular than the noise term, and the corresponding equation is not subcritical or equivalently super-renormalizable. So because in this talk, I assume that d equals 4, sigma belongs to the interval between 2 and 4. The value sigma equal to 2 corresponds to the standard dynamical phi-4 model in 4 dimensions, which is critical. So this value is excluded. However, the family includes equations which are arbitrarily close to the critical equation. The dynamical phi-4 d sigma model is closely related to a certain Euclidean quantum field theory model with quartic interaction term and a non-standard propagator given by the inverse of the fractional Laplacian. Formally, the measure of this quantum field theory model has this form, and it turns out that this measure is invariant under the dynamics of the dynamical phi-4 d sigma model. So this means that if we start the SPDE with a random initial condition that is distributed according to this measure, then the solution at any time t will also be distributed according to this measure. This fact can be used to give a reasoning, give a rigorous construction of this measure, and this was actually achieved by Gubinelli and Hoffmanova, at least for sigmas which are far away from the critical threshold. Models of this type also attracted some attention in the area of constructive QFT because for models with fractional Laplacians, one can hope to construct non-trivial fixed points of the renormalization group map. Another motivation to study these models comes from statistical mechanics. Singular SPDEs arise as scaling limits and describe macroscopic behavior of many models interacting with some random environment. It is plausible that the dynamical phi-4 d sigma model describes large-scale fluctuations of the long-range Ising model with the Glauber dynamics. Okay, in order to make sense of the dynamical phi-4 d sigma model, we have to introduce some UV cutoff. And to this end, we replace the white noise term by a regularized noise. My technique works for a very general class of approximations of the white noise, which need not be even Gaussian. The simplest possible approximation is obtained by convolving the white noise with some smooth kernel of a characteristic length scale of order kappa. So for every positive kappa, we can solve this equation in the space of smooth functions. And the goal is to prove that the limit kappa goes to 0 of the solution exists. It turns out that this limit exists only if the cubic non-linearity is appropriately modified. And in dimension 4, we need 3 types of counterterms. The mass counterterm, the counterterm proposed the gradient of phi. So generically, the limit kappa goes to 0 of the solution will only exist if the counterterms diverge as kappa goes to 0 at the specific rates. Let me mention that by imposing certain symmetries on the approximations of the noise, one can eliminate the counterterm proportional to phi square and the counterterm proportional to the gradient of phi. because of that, for simplicity, later in the talk, I will study the regularized equation with only the mass counter term. However, this extra assumption about the symmetries does not affect the proof. Okay, so here is the main result of the talk. Let phi kappa be the solution of the regularized phi 4 sigma model in 4 dimensions with a suitable initial condition. The first part of the theorem says that for some choices of the counter terms, the limit kappa goes to 0 of the solution of the regularized equation phi kappa exists. This is the so-called local in time solution theory. So this result does not guarantee that phi 0 constructed as the limit has infinite lifetime. There may be a blow-up at some finite time. So we would like to interpret phi 0 obtained as a limit as a solution of a singular SPDE. A potential problem with this notion of a solution is that it can depend on the choice of the approximation of the white noise. So this problem is addressed in the second part of the theorem, which says that the law of phi 0 obtained as a limit is parameterized by a finite number of parameters, such as effective mass, and is independent of the choice of an approximation of the white noise. So this is a universality result. Let me stress that there is still a finite dimensional family of solutions of a singular SPDE for a given initial data. And this non-uniqueness of a solution is closely related to the problem of renormalization ambiguities in quantum field theory. Okay, so are there perhaps some questions about the statement of the theorem?
Yeah, can I ask a naive question? So, so in this case, whatever theta is, how close sigma is to 2. So okay, when sigma is equals to this becomes 544. Which
yes,
is,
so then I cannot solve this equation.
Right, but even if sigma is very close to 2, you say that only mass counter term is enough to regularize this. But this is different from what we usually see in Euclidean quantum field theory, right? So does it mean that you
this
cannot?
Model is super-renormalizable. So
but
in models of this type, you do not expect that, for example, the coupling constant is normalized.
Oh, so okay. So you say that this is normal. Oh.
Yes, yes.
Okay.
But okay, in general, I need several other counter terms, like this counter term and this counter term. And they are eliminated only because of extra symmetries.
Okay.
So this is somehow accidental.
All right. So you can also reach stationary distribution by using this scheme and this renormalization.
So this is not possible because of this comment that I made.
Yes.
It's part of the statement. So this is only local in time solution theory. So this analysis, unfortunately, does not exclude a possibility of a finite time blow-up.
Okay.
And to say anything about the invariant measure, you will have to study long time existence.
Okay. Thank you.
Another question. This modification is only in the space direction, not in time.
It's both in space and time. However, this noise psi need not be a modification of the white noise. So it can be some approximation of the white noise, which need not be even Gaussian. So this works for a very general class of approximations, not necessarily approximations obtained by modification. By a simplest possible approximation is a modification.
Modification means convolution with a nice function.
Yeah, it's a convolution with some smooth kernel of characteristic length scale kappa.
Yeah, but only in X or also in T?
In X and T. So this kernel has characteristic length scale kappa in X, and let's say kappa to some power sigma in T.
Thank you.
Okay, so if there are no more questions, I would like to present the key elements of the proof of this theorem. So I first rewrite the regularized SPDE in the mild form. Ignoring for simplicity the initial condition, we obtain the following integral equation. G is the inverse of the parabolic differential operator that appears in the equation. I call this kernel the fractional heat kernel. Star denotes the spacetime convolution, and F kappa is the right-hand side of the regularized SPDE. And F kappa is called the force. As I said, my approach is inspired by the approach developed by Kupiainen. In particular, in both approaches, the fundamental object is the so-called effective force, which is a certain generalization of the force. And I would like to introduce this object now. To this end, let us consider the kernel G mu, which is the fractional heat kernel with some UV cutoff mu. And we shall rewrite the mild form of the SPDE as a system of two equations, one for psi and one for z. It is easy to see that psi and z satisfying these equations imply that phi given by the sum of psi and z satisfies the original equation. Moreover, we see that the equation for psi involves two UV cutoffs. So there is UV cutoff kappa in the regularized noise, and there is also another UV cutoff mu in the kernel. Because of that, the stochastic process psi lives on a spatial scales which are greater than both kappa and mu. In particular, for any positive value of mu, the process psi is not too rough, even in the limit kappa goes to 0. On the other hand, the cutoff mu in the equation for z appears in the kernel G minus G mu. Because of that, the cutoff mu plays the role of the infrared cutoff in the equation for z. And the stochastic process z lives on a spatial scales between kappa and mu. And as kappa goes to 0, the process z becomes very rough. Z is sometimes called the fluctuation field. So summing up, we split phi into psi and z. Psi is the regular part that lives on spatial scales bigger than mu, and z is the fluctuation field that is potentially very rough. Now suppose that we can solve the equation for z. The solution is a certain functional of psi. And now if we plug the solution into the first equation, we obtain the following equation for psi. This equation involves a certain functional f kappa mu. I call this functional the effective force. And the effective force satisfies the following equation. The effective force depends on two cutoffs, kappa and mu, and is a non-local functional of a test function psi. The cutoff kappa appears in the noise term. The cutoff mu appears in the kernel g minus g mu. Because of this fact, the parameter mu of the effective force plays the role of the infrared cutoff. It turns out that this expression that appears in the equation for the effective force coincides with the fluctuation field Z. And this field is very rough in the limit kappa goes to 0. Recall that the force F kappa contains a cubic nonlinearity. So we see that in order to define the effective force, we have to control potentially problematic products of the fluctuation field. On the other hand, because of the extra cutoff mu, the equation for psi is well posed even in the limit kappa goes to 0. Now let me list a few properties of the effective force. So recall that G mu is the heat kernel with some UV cutoff mu. The value of mu equal to 0 corresponds to no cutoff, and the value of mu equal to 1 is assumed to correspond to the full cutoff. That is, G1 vanishes identically. Using the equation for the effective force, it is easy to see that the effective force with mu equal to 0 coincides with the force. Indeed, if mu is equal to 0, then this term coincides with G, and this kernel vanishes, so the effective force is equal to the force. I claim that the solution of the original SPDE can be expressed in terms of the effective force with the infrared cutoff equal to 1 and psi equal to 0. Okay, to see this, we again use the equation for the effective force. So we set everywhere mu equal to 1 and psi equal to 0. Okay, this term by assumption vanishes. And then after convolving both sides with G, we get the following equation. Okay, and then using this as a definition of phi, we can rewrite this equation in the form phi kappa is equal to G convolved with the force evaluated at phi kappa. And this equation coincides with the mild form of the original SPDE. Okay, so summing up, the effective force with mu equal to 0 is given, and the goal is to construct the effective force with mu equal to 1. And the basic idea of the renormalization group approach is to construct the effective force in steps by gradually increasing the infrared cutoff. And to this end, one usually uses the so-called RG equation that I've written here. This equation is a generalization of this equation for the effective force. So in the RG equation, the effective force with certain infrared cutoff eta is given, and we are solving this equation for the effective force with some bigger infrared cutoff mu. So the original equation for the effective force coincides with the RG equation with eta equal to 1. So the approach developed by Kupiainen is based on the RG equation. So one constructs the effective force for discrete values of the infrared cutoff, starting from the value 0, for which the effective force coincides with the force, and ending with the value 1. At each step of the construction, one solves the discrete RG equation using the Banach fixed point theorem. Okay, I said that the effective force with 0 infrared cutoff is given because it coincides with the force. That is not completely true. So we know what is the form of the force. However, we do not know what are the correct values of the counter terms that guarantee the existence of the UV limit. So in order to find the values of the counter terms that guarantee the existence of this limit, one has to solve a certain inverse shooting problem. So one has to find some values of the coefficients of the force that guarantee that the effective force with unit infrared cutoff converges as the UV cutoff is sent to 0. So this strategy was successfully applied to the phi-4 model and KPZ equation by Kupiainen and Marcosi. However, their approach is not systematic, and it's not clear whether it can be easily generalized, or I expect that it cannot be easily generalized to equations close to critical. So in my approach, the effective force is constructed using a rather different strategy. So instead of solving discrete RG equation, I use the framework of the continuous normalization group, and my analysis is based on a certain flow equation that can be derived from the RG equation. So the flow equation is the equation for the derivative of the effective force with respect to the infrared cutoff. And this equation is supplemented with the initial condition that says that the effective force with 0 infrared cutoff coincides with the force. Note that I introduce a parameter lambda. So this parameter is used to organize various expansions and is set to 1 at the end of the construction. In order to solve the flow equation, I make the following ansatz for the effective force. I assume that the effective force is a sum of terms of order lambda to the power I. And each term in the sum over I is a sum of terms which are multilinear functionals in the test function psi. The coefficients that appear in these expansions, F, I, M, kappa, mu, are called the effective force coefficients. It turns out that the flow equation for the effective force implies a certain flow equation for the effective force coefficients. And using the latter flow equation, one can easily construct the effective force coefficients recursively. So the recursion is in order of ascending values of the index I, and for fixed I in order of descending values of the index M. And the recursion is based on the following three observations. So first, the coefficients with vanishing indices I and M coincides with the noise. And for fixed I, there are only finitely many coefficients which are not zero. Second, we can express the derivative of a coefficient with respect to the infrared cutoff using the flow equation in terms of the coefficients which have already been constructed. And the coefficient itself is constructed by integrating its derivative. Here I listed first a few non-zero coefficients in the order in which they are constructed. Okay, so let me perhaps remark that effective force plays analogous role to effective potential in quantum field theory. And this construction of effective force coefficients is analogous to a construction of effective potential coefficients. The construction of effective potential coefficients is the backbone of a very simple proof of perturbative renormalizability of quantum field theory models given by Polchinski. So my proof is strongly inspired by the proof of Polchinski. So as I said, our goal is to construct the effective force with mu equal to 1 and prove the convergence as kappa goes to 0. So to this end, we will prove certain bounds for the effective force coefficients, which are uniform in kappa and mu, and which imply absolute convergence of this series. And later we should study the limit kappa goes to 0. In this talk, I would like to concentrate on the proof of uniform bounds. So these bounds have the following schematic form and are proved by induction. So the induction follows the recursive construction of the coefficients. We first prove the bound for the derivative of the coefficient with respect to the infrared cutoff. And in this step, we use the flow equation and the induction hypothesis. So this step is straightforward. Then the bound for the coefficient itself is proved by expressing the coefficient as an integral of its derivative. Okay, so this works well only for the so-called irrelevant coefficients for which the exponent rho is strictly positive, because then we can use this formula for the coefficient and the bound for its derivative, after using this simple estimate, we get the right bound for the coefficient. However, this estimate only works for positive rho. There are finitely many terms for which rho is negative. We call such terms relevant, and we have to use a completely different strategy to bound such terms. And the idea is to represent such terms as functions of a certain enhancement of the noise. Okay, and here I indicated how I construct the enhancement. So maybe I'll skip that. And let me only say that in order to prove the bounds for the relevant coefficients, we have to establish certain bounds for the enhancement of the noise. And the bounds for the enhancement are proved using probabilistic tools. So they rely crucially of certain correlations between elements of the enhancement and follow from certain bounds for cumulants of the elements of the enhancement. And the bounds for cumulants are also proved by induction. So you can see that we prove the bound for the cumulant and the bound for its derivative with respect to the infrared cutoff. And the idea is to first prove the bound for the derivative with respect to the infrared cutoff using the induction hypothesis and a certain flow equation for cumulants. So this is easy. And then we establish the bound for the cumulant itself. That is the bound with S equal to 0. And this is again easy for irrelevant cumulants, that is cumulants with rho strictly positive, because then we can represent the cumulant as an integral of its derivative. Then we can plug the bound for the derivative and prove the right bound for the cumulant itself. This, however, doesn't work in the case of relevant cumulants for which rho is not positive, because then the bound for the derivative is not integrable at 0. The problem is with this boundary. So it turns out that the only relevant cumulants are expectations, which by the stationarity are numbers independent of the space-time point. And to bound these numbers, we impose certain renormalization conditions at infrared cutoff mu equal to 1. The numbers on the right-hand side of the renormalization conditions are arbitrary, and they parameterize the space of possible solutions of the singular equation. Next, we express the expectations at any value of mu using this formula. And then to get bounds for the expectation, we use the bounds for the derivatives of the expectations with respect to the infrared cutoff. Note that this time we avoid the non-integrable singularity at mu equal to 0 using the boundary condition at mu equal to 1. And actually the last formula with mu equal to 0 can be used to read off the desired values of the counter terms. Okay, so this is the outline of the proof. Summing up, the framework presented in this talk can be used to renormalize a large class of singular SPDEs in the full subcritical regime. I solved the renormalization problem using the flow equation. So this should be contrasted with the technique developed by Heirer and al., who use a diagrammatical representation and the variant of BPHZ renormalization. The flow equation approach is perturbative in nature. The solution is constructed as a series. The coefficients of this series are constructed recursively, and the series is proved to converge absolutely. At the moment, the method is applicable only to equations with polynomial non-linearities and additive noises. It would be nice to see whether the technique can be generalized to equations such as dynamical Sine-Gordon model or parabolic Anderson model. It would be also interesting to study long time existence and possibly construct the invariant measure. Thank you.
Thank you very much, Paweł, for this very interesting talk. I now leave the floor to the audience for questions.
Can I ask a question?
Yes, Hal.
So it's very interesting that you don't have to compute any Feynman diagram or anything, but still you get this, you can control renormalization. So what is the trick? Or of course, this does not work when sigma equals 2. Okay, so what is the difference for this, and how this?
There is a very similar approach to models of quantum field theory. And then in the context of quantum field theory, this technique can be used to prove perturbative renormalizability. And then this condition of subcriticality or super-renormalizability is not needed. So this also works for models which are barely renormalizable, for example. But it works in a sense of perturbative expansions without proving convergence. So this approach was already given in the 80s by Polchinski. So it's, let's say, an alternative to BPHZ renormalization that is based on diagrammatical representations. So there was already in the 80s this alternative technique that somehow avoids completely any diagrammatical representations and let's say algebraic and combinatorial problems.
But you have to compute somewhere, right?
Yeah, I think so. So in order to solve the renormalization problem, you need certain decomposition into scales. And this is somehow naturally implemented in this approach because of the use of this extra infrared cutoff. So there is this decomposition into different scales built in, and this is very useful when one wants to solve the renormalization problem.
Okay, thank you.
So actually, I had a question. So for 543, as you mentioned, there is the result of Gubinelli and Hoffmanova about long time behavior. I mean, so do you think your method could recover that result for the case of 543? You presented the theorem about small times, right?
Yes.
Do you think in the specific case of 543, the method could you know, be pushed to also get a global result?
Yeah, I believe this should be possible, even for equations close to critical, but this requires further analysis that I did not do in my work. So one would have to use some PDE tools like energy method or maximum principle. Then perhaps one could prove some a priori bounds that exclude the possibility of a blow-up, and then this could be used in the construction of the invariant measure. But this requires some further work.
Okay, thank you. Further questions from the audience?
Yeah, so that's, well, almost the same question. So you believe that this renormalization that you find here is enough for the global solution?
Yes, I do not think there.
Okay.
So somehow this, yeah, to establish global solution, you only have to prove certain a priori bounds that exclude the possibility of a blow-up.
Okay.
Paweł, you didn't define your Besov spaces, but so this is the standard definition, or it is. But anyway, does Hairer use Besov spaces as well, or?
Well, he uses a certain local version of best of spaces.
I mean, does it matter which functional analysis tools one uses, or it's really a secondary thing?
I mean, in my approach, I do not really use any tools from the theory of, let's say, best of spaces. So I only state the result using best of spaces because they are standard and probably known to many people. But somehow the whole construction is completely self-contained. I do not use any even standard results from the theory of best of spaces. Like, for example, the multiplication theorem, I do not need it.
Other comments? Okay, it does not seem to be the case. So let's thank Paweł again for this very nice presentation. Thanks a lot.